So I will first start with a little bit of introduction and how I get here today. So ever since I started my PhD thesis, all I wanted to do was to transform development environments from something like you can see on this image to extended development environment where you are not limited to the multiple monitors, but you can use and place the visualization or organize the workspace in the physical space around you. One of the big pros of something like this would be that you can actually move your workspace everywhere with you without moving all the monitors and stuff like that. And the sort of the research question I have is whenever there is enough knowledge encoded in actual organization of such an environment, that this knowledge can potentially help newcomers in some IT company. So very first prototype I did in such area was extension of Visual Studio Code. So here I can just from the context menu ask for visualization which are around me. It's basically just the UML diagram and in combination of the city metaphor. And you can see the metrics of the source code or navigate in your project through this. The first prototype was very simple, but it was good to actually show or find out what are the biggest problems. And the first prototype was done for Meta 2 headset, and there were some shortcomings which were threats to potential evaluation, which is really important for me because of the PhD thesis and research area. And the biggest shortcomings with Meta 2 was basically the poor tracking, the positional tracking, the poor hand tracking or way of hand interaction, and the really big discomfort while using this headset. So the first two I try to solve or minimize by using or integrating the Vivebook or the Vive tracker, which has better tracking than the original Meta 2 approach. And for the hand tracking, I use the Leap Motion. Luckily, at this point, the Project North Star came out, so I was like, okay, this is just silly. I would rather use Project North Star, which is basically the same thing because I was just using just the displays and combiners of the Meta 2. And in addition, by adding the Vive tracker and the Leap Motion, I even made the discomfort worse. So that's how I get actually to the Project North Star. And even though I actually was possible to minimize the 2 or 3 shortcomings, it still wasn't enough to get any sort of reasonable evaluation. The reasonable evaluation I actually expect to do is a comparison with traditional approaches. And it doesn't matter if I use time correctness, user experience, or usability, any of these will be shredded as there are still problems either with the tracking or hand tracking, hand interaction, and so on. So there were 2 things that I can further do, and that's either improve the experience by improving the calibration, either the between sensor calibration or the optical calibration, and by adding the eye tracking, which is still necessary for the 3D calibration. So each user does not have to manually tune the parameters, IPD parameters we already have. The eye tracking is also quite useful for the gaze tracking because I can get more insight why this approach was worse or which particular area have poor performance. So this is basically the reasons why calibration and eye tracking and gaze tracking are so important for me. So first of all, I started with the between sensor calibration, where I actually tried to do automatic approach, so you don't have to align the lip motion by using the semi-automatic procedure where you're trying to align your hand with the virtual hand. And basically, what I was doing, or I tried two approaches. The first one is based just on the ATPEAK board, which is seen by all three sensors. One sensor is basically for the optical calibration as well. Second one is lip motion, which we use for hand tracking, and the third one is a tracking sensor, in this particular case T265. It doesn't really matter that they are not in the correct spot. It was just for proof of concept prototypes. And the other prototype I did is based on traditional OpenCV stereo calibrate method. So here you can see the three windows. Each is for one sensor. So one is for T265, one is for Z-Mini, and one is for lip motion. They all track the same ATPEAK board, and based on that, I can get the relative offsets and translations and rotations between them, which is basically all I need to align them properly in Unity, so the experience is optimal, I would say. Of course, this was just a prototype, and it's not good practice to base any kind of relative offsets on single observations. So definitely there is a future world where I will do multiple observations and do some kind of optimization. But even though the results were pretty good, and I actually compared them to the stereo calibrate method, and the variation there was just under 1 millimeter. But of course, the problem is that you need to position the board in a way so as many ARUCO markers are visible to the camera and tracked by camera to achieve really good results. So the second approach to the between sensor calibration was based on the OpenCV stereo calibrate. Again, I took two cameras. For example, the upper one can be T265 and the bottom one can be lip motion. And you basically create a virtual stereo pair, which takes left camera of the T265 and left camera of lip motion, and treat this as a vertical stereo camera. Then you just show this board pattern to those two cameras and do the traditional stereo calibration procedure, which will give you basically the translation and rotation between the left camera of the T265 and the left camera of the lip motion. Given that both of these sensors are factory calibrated, I use the CalibFix intrinsic flag, so it does not try to optimize distortion and I'm not sure what's the second one, and camera metrics, because these are already known from factory calibration. And as I said, when I compared the results of these two, there was a variation just under 1 millimeter. I try also many alternative boards. The one that might be interested was DodecaPen, which is basically just ARUCO board wrapped to the dodecahedron, and it's not interesting in terms of between sensor calibration, but it might be interesting to create any kind of controller. The original paper, which was this taken from, uses this kind of board or tracking technique for basically drawing. So this was stick to the top of the pencil, and they got quite good results. From the perspective of between sensor calibration, it yields relatively good results, but only when at least 4 faces of the dodecahedron was visible. and there's basically no advantage against the Aeroco board, as there is no problem to get all 9 Aerocos to be tracked by all 3 cameras. But as I said, if anybody would like to experiment with this for the means of controller, 3D printed controller or something like that, might be useful for them. Also, there's a problem with 2.65 and the resolution and the field of view. You will probably need to make this even bigger than I did to get any reliable tracking at that distance. Once I was happy with the results of between sensor calibration, I was willing to try them. But I ran into problem with the optical calibration, as I cannot confirm purely visually, if everything was aligned properly or not, because it turned out that the 2D calibration was not working as I expected. I figured this out during the refactoring I did on the 2D calibration method, and the things I did there during the refactoring was that I add abstract class, so other stereo cameras can be easily added, so it can be easily extended. And I also do synchronization of frame capture with rest of the code, so it can run much more quickly than the original approach. The problem I mentioned I ran into was there was actually 2 problems. The first one, which is visible on this image, is that my refactored version yields different results. You can see that the Z camera frame below looks better than the top one, and this was caused by the fact that I actually undistort the images before I calculate the gray codes. So that was the only difference I did in the code, and it seems it is much more reliable to undistort the images before you capture the gray codes and create the gradients. Here is also a comparison. The red is basically this, so if it is red, there is also some tolerance, but if it is red, it is significantly different. And this is basically the difference when I use the undistorted versus post-undistorted. So with one approach, I undistorted the image and then do the calibration, then do the calibration and capture the gray codes. With the second approach, I capture the gray codes and then did the undistortion. So the reason why this is happening, or at least I think it's the ATPEAK precision. I'm not sure how well you can actually see this on the screen share, so I do a little bit zoomed image over here on the top, and you can see the stripes over here, and that's caused by the fact that you have only 8 bits to actually encode these gray codes, and when you actually try to undistort this with a limited precision, you just multiply the error, and then the polynomial fitting we use during the calibration might not be optimal. So I mentioned we have 8-bit precision using the gray codes, and my first idea was basically to improve the precision by dividing the pattern even more, but I quickly realized that you cannot do something like that because you're limited by the resolution of camera and the resolution of the monitor. In this particular case, the resolution of the monitor was the real limiting factor. So if any of you are not familiar with the 2D calibration, the principle is pretty straightforward, I would say. I was really afraid of it, but once I finally understand how it works, I realize it's beautiful and easy. And basically, what is happening there is that by showing those gray codes, you can figure out the mapping between the screen coordinates to the camera coordinates, and using the camera calibration, you can figure out the race between any, let's say, screen point and the camera. So by this, you can actually figure out the distortion caused by the combiner while the screen image gets projected in your eye. So that's to the calibration part, or how to figure out the distortion. And here is actually the reverse process, how it's done in ASCII. And basically, you are using these rays and trying to project the screen points using the polynomial fitting we did here. So basically, you have a virtual camera in Unity scene. You know what is the image you want to show to the user, and you know what kind of distortion needs to be applied. And once you do this, you can actually show to the user what they should really see. So apply the proper distortion to the image so everything looks correctly. So why I am speaking about this process is the second issue I run into, and that's basically the eye offsets, which are in ASCII. And the problem was that I cannot even validate visually if the outcome of 2D calibration is correct, because what I see after the 2D calibration doesn't look right without manually tuning those eye offsets. And any kind of manual tunement is basically ruining any kind of visual confirmation whenever the between sensor calibration approach is correct or not. Why I know that the output or the calibration is not correct without applying the eye offsets is that basically your view gets cropped, which is illustrated by this red line. And when you apply the offset, which basically just move the UVs, then this image will move more to the right, and you actually see what you really should. So then I moved to the actually trying to figure out those offsets and trying to calculate them automatically. I get to the state where I was actually getting really good results for the left eye and for the right eye. No matter what kind of camera I use for the 2D calibration, so I get persistent results. But although everything looked correct using the left eye and the right eye, the stereo vision breaks. So when I was using both eyes simultaneously, the image didn't look right, because either there was some issue with relative distance, like IPD, or there was issue caused by the rotation itself. And I just suspect that this is caused by the fact that the camera we are using is not perfectly centered to the screen. So those rays are never centered to the viewport, but actually the rendering we currently use is for the V2, I think, does expect this to be. And you can actually somehow minimize this issue by the eye offsets. That's the one case, but I think there also needs to be applied rotation. It's not just an offset thing, but I think it's also a rotational thing. So if anybody would have ideas regarding to this, I would be happy to hear them out, because this was basically the breakpoint where I stopped trying to figure this out or figure out this problem to the calibration and move back to the 3D calibration. But once I get to the 3D calibration, I soon figure out why I tried to ditch it in the first place and move to the calibration. So I was kind of looping myself. So the first big problem for me was that it requires two stereo cameras, and more particularly, it's also bound to the ELP cameras, and these are not factory calibrated. And I have a great issue getting a really good calibration for these two cameras, and basically one was really problematic, and up to today I never did any reasonable calibration. And that was kind of again a break point for me when I was okay, I don't want to use non-factory calibrated cameras anymore. So let's try again to refactor the 3D calibration to allow to use any kind of camera, stereo camera we have or we would like to use. And another problem regarding to the 3D calibration, that it requires external monitor, which I didn't have also, and it was during the COVID breakdown in our country, so I wasn't even able to try home for my external monitor. So I was like, okay, let's do about this something too. So again, I start some refactoring. I first try to eliminate the hard-coded parts. This is basically regards to the fact that the bottle camera is flipped during the calibration because it's upside down. It's rotated 180 degrees. And this is one of the things that are hard-coded all over the current 3D calibration code. And another problem was that as I was trying to add support for different cameras, I basically tried to solve the support by creating a REST cam, which basically uses service and REST API to expose the frames from basically anything to Unity. In this particular case, I use Python, which was pretty nice with either OpenCV cameras, T265, or anything else I run into. So it was really easy to get frames, and it is also really easy to handle REST request in Unity. The possibility to avoid camera calibration by design means that as you can use different cameras, you don't need to do the camera calibration yourself, as many of them are already factory calibrated. Even before I did finish this, I came to the idea that we can use virtual cameras, and that was basically, or the idea of the virtual camera is based on 2D calibration, because you remember the 2D calibration basically gives you the mapping between the screen and the camera image. And so by using the output of the 2D calibration, you can figure out what would the camera image look like if you know what the screen look like, which you know, because you can render the content to the render texture and then apply the distortion, and then you have actually the true or accurate representation of the camera image, even without having the physical camera running at that time. Why is this good? Is that this allows you to do the 3D calibration just by using one stereo camera. You don't need to have two of them, and you also don't need the external monitor. So these are two really good pros of using something I call virtual camera. But to construct the virtual camera, you basically need to do two passes of 2D calibration. The first pass is to figure out the camera to monitor mapping. So if you know what you are showing on the monitor, you will be able to see what the camera image of the monitor will look like. So if I have any kind of stereo camera in the front of my monitor and I run this to the calibration pass, I can figure out the camera image. If I send to the procedure the real screenshot of my screen. Of course, the 3D calibration was done from two positions, so each of these two passes needs to be done twice. Once from the top position and second time from the bottom position. For these purposes, I created a really easy to print and assemble T265 holder, which by using which you can easily move T265 from the bottom position to the top position, and it gives you pretty persistent placement because there are these circular holes and gravity pushes the T265 down, so it settled down pretty well. And there is this front clip which minimize any kind of wobbling on the other axis. So this gives me a really good and easy to create way of moving the stereo camera from bottom to top position. And once I did the camera to monitor to the calibration from this two position, I moved to camera to pen as screen calibration. So basically, I need to do the same thing again, but I need to put the Project North Star headset on the calibration rig. That's probably the worst part of such calibration because you need to be sure that you didn't move anything. Swapping the camera between the two positions isn't problematic, but putting the headset on the rig without moving anything kind of was. So I glue everything together. But that's something you need to do during the 3D calibration too. So that's not a drawback compared to the original calibration. Once I have these two mappings or these two the calibration outputs from two positions, so I have in total 4 calibration outputs. I need to solve somehow the 8-bit precision problem because once I will use the remap to calculate OpenCV remap to calculate the camera image or what would the camera image look like, the 8-bit precision would not be enough. But given that these are just basically linear gradients, because I use already undistorted images, I use them for the reasons I mentioned before, it is really accurate to just use selective Gaussian blur. So basically what I just did with 8-bit images, I convert them to 16-bit images and apply selective Gaussian blur, which eliminates the vertical stripes and get pretty or very good estimation of higher precision image without using gray codes from higher depth. Okay, so once I got these 16-bit gray codes, you just need to somehow in original Unity code figure out what is the image you want to distort or on which you want to apply the distortion given by the 2D calibration output. So basically, you just need to render monitor pattern camera from the repository to the render texture one. So to some render texture and render the combined display camera to the second render texture. Then you just apply OpenCV remap, where input are the 2D calibration outputs obtained before, and you basically have one-to-one image of the camera without using any camera. So here basically the comparison between the virtual and physical camera. The physical camera image is the one when you don't see much, which wasn't a really good image to take, but it also illustrates that virtual camera also solved many issues regarding to the exposure and other problems. For example, even using the gray codes, you got some glare effect from the monitor because it's a high contrast image. And basically, when I compared the calibration pattern, again, virtual versus physical camera, you can see that the only difference there is just glow related or exposure related. Once I actually integrate this to the original 3D calibration repository, I was able to run a full calibration procedure. Again, as you see, as this is executing, there is no physical camera connected to my computer, and everything you see, it's done basically just based on 2D calibration out. So basically on 4 2D calibrations done before. And also you don't need external monitor connected because everything is rendered to render texture. And screen to monitor mapping you need to do before you can be easily done using your main monitor. So the need of external monitor was completely eliminated. And also the need of a second stereo camera. However, I'm not finished here also with the 3D calibration because I'm still finding some, say, hard-coded things in the project, the 3D calibration Unity project. For example, in even the distance between top and bottom cameras or the translation between them is, at least it seems it is hard-coded, and it does affect the actual calibration result. And so the best I achieved so far is on the following image on the screen. And you can see I'm still found for the optimal case. But you can also see how virtual camera solves another issue. You usually have not perfectly colored image, but you have some kind of gradient based on camera properties. But here you can perfectly get the original patterns. So everything is either gray or the intersection is perfectly white. So there is a great place for alternative optimization techniques, or maybe even trying to simplify some parts of the calibration. Another thing good about virtual camera is that you are not bound to the frame rate of the camera. And basically, if you synchronize again the frame capture with the rest of the code, you can actually run the calibration really fast because the OpenCV remap takes like I don't know, maybe 5 milliseconds. So you can have still a pretty good frame rate. Reading the render texture using suitable methods, it's can be done even at 400 FPS on my computer using the asynchronous. I'm not sure what's the exact name in the Unity, but basically I'm trying to asynchronously get the image from the graphics side to the CPU side. So using this in the combination with the texture load, the raw texture data, I was able to achieve even 400 FPS on my computer. And in combination of the OpenCV remap, you still have really good FPS. So basically, each step of the 3D calibration is then limited only by the FPS of your application. So you can even try much more positions of the screens with respect to the eyes and combiner, so you can easily figure out even non-standard builds of Project North Star. The eye tracking would be quite a different series, I would say. So I definitely won't be able to go through all of this, not in detail. So I will just say what was done, and I will talk about this also because it is related to the calibration, and you also need to calibrate the eye tracking camera somehow. So very first thing I done is over here. I create the custom eye tracking, uh, which basically wasn't made for the Project North Star, uh, not for the integration, but I select the camera placement, which I later also applied to the Project North Star. So it's basically the same, but it was easier to develop it this way because PupilLabs need external camera to do to the calibration of the eye tracker. So this was the easiest way to first evaluate it under control options or in control environment, and then move and compare it after the integration to the Project North Star headset. You can see the cameras over here, but basically these cameras also need the drivers, which I was able to fit to the Leapmotion pad. So the whole integration doesn't add any additional space or significant space. The original headset, everything is hidden behind the Leapmotion, and I was even able to fit the cables around the display board. So another problem, as I mentioned, is that you either need to solve the camera position with respect to the tracking camera or Project North Star headset, or some origin of the Project North Star headset. And the very first, then maybe naive approach I tried was that I have a snappable ergo boards, which I was able to easily snap on the eye tracking cameras, which are in the front, and it gives relatively good results. And this is basically the video of my eyes being tracked by those cameras. So this is basically real-time position of my eye with respect to the Project North Star headset, and it's relatively accurate, or the accuracy is affected mainly by the precision of the camera calibration, and by the camera calibration I'm figuring out the placement with respect to the headset. I mentioned the first prototype. This is basically the video of gaze tracking using this prototype, as I'm looking on stuff around me, which already gives really good results. But the problem is that this is calibrated using the video feed from the webcam that was attached to this prototype, and it uses points shown on the laptop screen in the front. So this cannot be used directly, or you don't want to use this directly using the Hotstar headset. And if you would try to do such calibration using the headset screens, it is the precision, the overall precision would be given by the quality of your optical calibration, which I was still struggling either with the 2D or 3D approach. And another problem is that such calibration needs to be done each session. So every time you put the Project North Star on your head, you will need to do, I think it's 27-point calibration in 3, or it's 9 points in 3 different depths. I'm not sure, but it's a pretty annoying thing to do each session. On the other hand, this approach, which is based, I will add important fact here. This calibration requires the webcam but it does not require to know where your cameras, eye tracking cameras, are in space relative to anything. So this is solved during the per session calibration. In here, I did different approach where the position of camera is required, but on the other hand, the user does not have to do the calibration of the headset each session. So you need to do some special effort to figure out the camera placement, but once the user do the initial calibration to figure out the optical to visual axis rotation, then he is free to use the headset or use the capabilities of eye tracking and gaze tracking. Just the gaze tracking without any other calibration. The eye tracking you see over here is calibration free already. Just the gaze tracking requires the calibration. As I said, in this particular case, it will be just one time calibration per user. You will store that calibration, and then if you load it, you're just free to use the gaze tracking. That's basically what I just said. I just didn't remember I have slides for that. And so each of these effort I did, it's basically aimed to my, I would say, ultimate goal, and that's to basically design and implement all-in-one calibration method, which would interconnect all these things I mentioned, and in the end of the procedure, it will give you the relative offsets or translation and rotations between the tracking sensor, the lead motion sensor, the position of your eyes, which would be derived from 3D optical calibration, and also the position of the eye tracking cameras. Given that I will be using a camera which will be swapped between two positions, the rest of the space can be used for any kind of small Arco board, and thanks to that, I can also figure out the position of these eye tracking cameras without attaching any Arco boards on the cameras, as I did before. So basically, this over here will be obsolete, and I will just attach some boards here to the rig. And that's basically the ultimate goal of anything I'm trying to achieve. Okay, so thank you very much for your attention. That's basically all of my presentation. And if you have any questions, feel free to ask or write them down in. So I forget to talk about many things. One of them, if there are any questions, just feel free to interrupt me. But once I get to them, there was also some effort by using the low resolution sensors, and I completely forget to talk about this. Even I have few images over here, and I'm talking about the PixArt sensor, which are really affordable. It's just few bucks for each of the sensor. And the only limitation is that the resolution of the image is really low. It's 30 by 30 pixels, so in total you have only 900 pixels. But even using such low resolution things, we were able to find existing approaches which are based on gradient methods to get relatively good pupil tracking. And we also tried the neural network approach for the super resolution. And this is the real image, and this is the image we get from the super resolution neural net. It's not perfect, but basically it just serves as a proof of concept that there is not enough information encoded in such small amount of pixels. And as you can see, although this should be the same, the pupil itself get deformed by the neural net. So any kind of sphere fitting using for figuring out the eye model or the position of the eye not be viable, and I don't think that any case tracking be directly applicable. But there is also possibility to move to the iris tracking, not the pupil tracking, which would be for sure better alternative. But I'm not aware of many already available approaches or open source projects which done any kind of iris based case tracking really reliably. On the other hand, the things I'm using are all based on the PupilLabs, which is also open source project, and it was just straightforward use without re-implementing anything. I'm not sure. So I will read the question. So you have to calibrate every time you put it on. So would that be part of the initialization of the North Star unit? Well, this depends on the final calibration procedure that will be selected, and I believe we are talking, or you're asking just about the eye tracking. Am I right?
Yeah, you're right. Sorry about that.
Okay. No, it's okay because I mixed a lot of things together, so I wasn't sure. So regarding to the eye tracking, purely eye tracking, you don't need to do any sort of calibration as a user. But if you want to use gaze tracking, then depends which approach we would use. If we use the approach in which the camera position is known, and we will use the PupilLabs software or something similar to that, then you need to do just one-time calibration and store that somewhere. Because even if you know where your eye is, which is calibration free, you still don't know what is the difference or what is the offset between your visual and optical axis. And that's something that needs to be figured out for the user by using, again, the endpoint calibration. But this needs to be done only once and stored. And any other session, this will be automatically loaded. You just need to select the profile of a user. And then if everything would go right, everything also seems right through the headset, because this will also adjust anything that is based either on the gaze tracking or on the eye tracking. Okay.
So, right, the question though I was curious about, and it's like a follow-on, is it almost seems like if you automate this, could you also do it in a fashion like using machine learning to possibly figure out all the positions? And I don't know, I may be talking gibberish here, but I'm using some machine learning algorithms at my work right now to figure out malware, right? I'm in security. So I was curious if you had gone down that path where you're going to try to figure out the different positions, and if there's a way with the calibration, the 2D and the 3D, that you could feed this in and figure out the optimal calibration, like automagically, so to speak, through the code. When somebody puts it on, you could ask them questions like, do you see this lining up correctly? And it would be obvious to them, and they would say yes. And then you could keep, is this better or this is worse, kind of stuff. And through a series of questions, you could auto calibrate it that way. Does that make sense?
Yes, it makes, but I'm afraid that something like this wouldn't be possible. I mean, there are two cases. Either you buy the headset and that one is already calibrated to the point you don't need to do any calibration as a user.
Mm-hmm.
And the only calibration you need to do is related to the gaze tracking and to visual optical axis. And the second case is that you want to build yourself the headset and you want to calibrate it. And given what I saw during refactoring of the 2D and 3D calibration and somehow checking this in general, I don't think anything of this can be done automatically. I just don't believe so. I don't think there's any kind of machine learning magic which would be able to do that. I
Okay,
mean,
cool.
clearly,
I was just asking. Yeah, I didn't know.
theoretically, if we give you some kind of real thing or some kind of something like Aruka board or some object like that, and we would know that you are following it with your eyes, maybe something like that would be possible, but that's not far from the between sensor calibration. You also just show Aruka board to it, but this way I can imagine it can be done by giving the user some kind of printed marker or something like that, and he is asked to follow it by eyes and move it around.
Okay, cool. Thank you.